In this lesson, we're going to talk about how to solve systems of equations by elimination. We're going to revisit the definition of systems of equations. We're going to look at those properties of equality, and then we're going to add and subtract to eliminate. Let's remind ourselves of the definition of systems of equations. Systems of equations are two or more equations with the same variables. They both have x and y, or one of them has x and the other one has x and y. They have the same variables. A solution to a system of equations is the point xy that makes both equations true. There are multiple ways to solve systems of equations. As we've talked about before, you can solve by inspection, just by kind of guessing and checking. You can solve by graphing, elimination, substitution, and you can even use augmented matrices. This is where the problem solving comes in. Technically, I can use any of these methods at any time, but there are certain problems that are better suited for better methods. This one is great for graphing because it's already in slope-intercept form. This one, however, is not already in slope-intercept form. I could put it in slope-intercept form, but it's not great for graphing because when it's in slope-intercept form, the y-intercept is a fraction, which makes it difficult to graph. So we need to pivot, and we need a new method to solve this. And that's where elimination comes in. This one is set up beautifully for elimination. Before we dive into the method of elimination, let's talk a little bit about why it works. So you'll remember back from linear equations that the properties of equality state that we can add equivalent amounts to both sides of an equation and it remains equal. We can also remove equal amounts from both sides. I can add an elephant to both sides of this scale, and as long as the elephant is the same weight on both sides, it's still balanced. If the elephant was equal to a hippo, I can add an elephant to one side and a hippo to the other. If they weigh the same, I can still add both of them to the same side, and it is balanced. Let's look at how that applies to elimination. We're going to go back to that original problem in a little bit, but I wanted to start with one that's a little bit simpler. So we're going to solve this system of equations below. The first thing to notice is that negative 3x minus 2y is equivalent to 8. So this is my elephant and this is my hippo, and they're equal in weight to each other. That's what that equal sign means. So I could add 8 to both sides of the equation and it would remain balanced. I could add negative 3x minus 2y to both sides of an equation and it would remain balanced. Or I can add negative 3x minus 2y to one side and 8 to the other, because negative 3x minus 2y is the same thing as 8. This is my elephant and this is my hippo. So I can add negative 3x minus 2y to one side and 8 to the other of the top equation. So I'm going to do that. I'm going to rewrite this equation right here. Just so I have more room. And then I'm going to add negative 3x minus 2y to this side of the equation. And then I'm going to add 8 to this side of the equation. So I'm adding something that's equal to each other. So 8 is equal to all of this. So I can add them both to both sides. And the reason why I do that is because the negative 3x and the 3x are going to cancel each other out. And then all I'm going to have is negative 2y plus 4y equals 18. And now my equation is all in one variable. Do you see that? And we know how to solve that. We combine like terms and then divide by 2. So y equals 9. Now, we have y. So remember, the whole goal is to figure out the x and the y that work in both equations. So I have y equals 9, but I don't know what the x is, but I can figure it out. So the way I do that is I go back to one of the original equations. Like I've figured out one key that I can plug in here, and now I can figure out the other variable. So 3x plus 36 equals 10. I have 36 and 10 are like terms, and I want to get it on the other side. So I move it, I switch signs so that I can get those like terms on the same side, and I get negative 26, and then divide both sides by 3. So x equals negative 26 over 3. And this is my answer, negative 26 over 3, comma, 9. Remember, when you get your y, you have to substitute it back into the original equation to figure out what x is. You're not done until you have both x and y. Now, that seemed kind of weird to me that I got negative 26 over 3 and it seemed a little awkward. So the best thing about systems of equations is that you can know whether you have the right answer or not because you can check to see if it's true. So let's do that real quick. Remember, if it's a solution, then it makes this equation true. So when I plug negative 26 over 3 in for y and 9 in for, or I'm sorry, negative 26 over 3 in for x and 9 for y, do I get 10? That's a question mark equals at this point. And you can type that into your calculator and you see that you do in fact get 10. Then you also want to test it in the second one because it's probably going to work in the first one since I used that to figure out what my x is, but it may not work in the second one if I did something wrong. But if you type that into your calculator, you do, and remember this is a question mark, you do in fact get 8 equals 8, and so that is the solution. Over here I have the steps that I just went through. First, look and see, are they both in standard form? Elimination works best when your x's and your y's are all lined up. So if it's not in standard form and you want to use elimination, you can put them both in standard form in order to make it elimination. You also want to just make sure that your x's and your y's are lined up. Step number 2 is to look for opposites. The reason why this worked is because the 3x and the negative 3x are opposites that canceled out when I added it to both sides of the equation. So if you have opposites, then elimination works really well. If you don't have opposites, you could make them opposites, but we're not going to go into that in this video. Then you add the two equations together. You solve for the remaining variable. So one of them is going to cancel out. You're going to solve for the remaining variable. You're going to substitute that remaining variable back into the original equation and solve for the other one. So in this case, we solved for y, and so then we substituted our answer back in for y, and then we solved for x. And then you write it as an ordered pair. Let's do one more example, and I'm going to do it just a little bit differently this time. So on the last example, I rewrote this, and then I put the equations, I added it to both sides. But instead of doing that, I'm going to actually just add them right here. So first I'm going to look, are they both in standard form? They are. I have ax plus by equals c, ax plus by equals c. The x's and the y's are lined up. I'm going to look for opposites. I don't actually have opposites here. I don't have 2 and negative 2 or 5 and negative 5 or 9 and negative 9, but I do have the same number. So on this one, if I add these two together, I'm going to get 4y and negative 4x, and nothing's going to be gone. But if I were to subtract them, then 2y minus 2y would cancel out. So that's what I'm going to do, is I'm going to actually subtract, and I'm going to subtract everything. So I'm going to subtract the negative 9, I'm going to subtract the 2, and I'm going to subtract the negative 11. So 2 minus 2y is 0y, and that's good because that's what we wanted. We wanted for it to just go away. 5 minus a negative 9 is 14. Remember, double negative makes that a plus. That's a weird looking plus, isn't it? 14x equals, and then 5 minus negative 11 is 16. And this is the same problem that we looked at in the example at the beginning, the one where I put them in standard form and the y-intercepts were fractions. So I get 14x equals 16. Divide both sides by 14. I'm solving for the remaining variable. So I did this, and I did this, and I did this, and now I'm solving for the remaining variable. And I get, I'm going to simplify that fraction, 8 over 7. X equals 8 over 7. Seems kind of weird because it's a fraction, but I didn't do anything wrong, so it must be right. Now I'm going to substitute that back into the original equation. So eventually I'm going to have an ordered pair, and I have the x, I also need the y. So keep in mind, you have to have the x and the y. So I'm going to substitute the x into the original equation, and it doesn't matter which one you use. I always use the top one. So I'm substituting it into 5x plus 2y equals 5. 5 times 8/7. I'm using my calculator. Is 47. I guess I didn't need to use my calculator. I don't know why I was hoping that would simplify. You were all hoping it would simplify too, weren't you? I'm going to move this over to the other side so that my numbers are all on the same side. So I'm going to switch sides and switch signs. I'm going to pull up my calculator again and subtract 5 minus 47. So 2y equals negative 5/7. And then I'm going to divide both sides by 2. So negative 5/7 divided by 2. I'm going to use my calculator to do that too. And I get y equals negative 5/14. I solve for the other variable, and I'm going to write it as an ordered pair. And here is my answer. And I didn't put a step 8 on this one, but it's always a good idea to check and make sure that you are right by plugging those back in for x and y to see if it equals 5. And I'm going to leave that for you to do.